Now, two more concepts that we want to get, each of which has their own objective. In Objective 4, we're going to be asked to describe the thermodynamic principles that are important to understand human biology. So we're going to talk about energy conservation. We'll talk about potential and kinetic energy, endergonic and exergonic processes, entropy and diffusion. So the first thing we're going to use as a definition is the definition of potential energy versus kinetic energy. Potential energy is where energy is coiled up like a spring, or in this example, like a strung bow that's about to give energy to the arrow. So this potential energy is ready, that's why it's called potential energy, but it hasn't actually happened yet. Then we're going to turn potential energy into kinetic energy by letting go of this string in a bow, or letting go of a spring, or in the case of, for example, being on a mountain and snowboarding, when we get to the top of the mountain, we're full of potential energy. When we start to turn our face down the fall line and turn that potential energy into kinetic energy is when we start moving. So as we're moving, we're calling that kinetic energy. The word kinetic means for something to move. So I'm changing my potential energy up here at the top of the mountain to kinetic energy as I slide down the mountain. So these are all examples of converting potential to kinetic energy. These are two forms of energy that are interchangeable, as you can see. So we can turn kinetic energy by winding up the spring on a clock, for example. We can turn kinetic energy into potential energy. We can turn potential energy back into kinetic energy. That leads us to the concept of endergonic and exergonic reactions. When energy has to be supplied to a reaction in order to make it go forward, then we call that an endergonic reaction. What I want to do is take a little bit of time to go through this. These are our graphs that we're also going to look at in Module 3, but it'll be easier to understand them in Module 3 if we take a little bit of time to look at them now. What we have on the left-hand side of this graph, and I'm going to try to activate the pointer here. I hope you can see my pointer here in the lower left-hand corner of the screen. It just went away, but I'll bring it back. Is reactants. So this is what's going into a chemical reaction. Then there's going to be some energy that's required to get those two reactants together. And finally, there's going to be an energy that's tied up in the products. If the energy that's tied up in the products is greater than the energy that's tied up in the reactants, then that energy has to come from somewhere. That energy has to be supplied. And because we're putting energy into endergonic, because we're putting ergon energy into the reaction, we call that endergonic. This is a reaction that needs energy put into it as the chemical reaction moves forward from left to right as we look at this graph. We call those kinds of reactions in our body anabolism. This is the process of storing energy in chemical bonds. For example, bodybuilders will take anabolic steroids, store a lot of energy in the chemical bonds of their muscles, and then that energy can be released when they need to do their weightlifting. Catabolism is the opposite process. Catabolism is exergonic, it releases energy. In this case, the energy that's tied up in the products is less than the energy that was tied up in the reactants. We still have an activation energy barrier that we have to get over. We still have to put energy into the system to get from reactants to products. But as we do so, then we're going to release energy. That's why it's called an exergonic reaction, because exo means that things are coming out of. So energy is coming out of this system. So we call this an exergonic reaction. This is an example of what scientists would call, physiologists and biochemists would call catabolism. This is energy being released from chemical bonds, and this energy is being turned into work. We'll discuss this a lot as we go through the course. So this is a basic concept that I think you want to nail down at this point in the course to make it easier to understand later on. We're going to use this model of reactants and activation energy in products many, many times as we go through the course, but particularly we're going to spend a lot of time on it in Module 3. So it's, as I said, best if we understand it now. Now, the other concept of thermodynamics that we need to have in our quiver of arrows before we go through the course is the idea of entropy. This is the idea of disorder in the universe, and you may or may not know the law of thermodynamics. We don't need to be able to quote it for this course, but you do need to know that entropy is increasing, that disorder is increasing. Entropy is just a measure of disorder. So we can see as we go from left to right on this slide that we go from a highly ordered system to a disordered system. A highly ordered system would be a jar full of atoms that are all sorted out into blue atoms and yellow atoms. A highly ordered system would be bricks that are stacked up in an orderly array. Houses don't clean themselves. Atoms don't go from a disordered state to a highly ordered state on their own. Bricks don't go from a pile of bricks to a neat stack of bricks on their own. In order to move from right to left in these diagrams, we need to put energy into the system. So to overcome entropy, we have to add energy. In the absence of added energy, things will become disordered. And that's what we mean by the red arrow saying that this is a spontaneous change. So the spontaneous direction is for an increase in entropy, and that's what's shown on the right-hand side of this slide. So yellow atoms and blue atoms all mixed together in this jar would be a disordered system, and that would be an increase in entropy as we move in the direction of the red arrow. Bricks that are just laying in a jumble are a disordered pile. That would be an increase in entropy if a wall fell down and made a pile of bricks where there previously was a neat stack of bricks. So all we're saying, just to reiterate, is in general, as we look at this slide, things don't move from right to left without an input of energy. Things always move from left to right if we don't have any energy input. If we want to move in the opposite direction from the red arrow, then we need to put energy into the system. For example, this man shown at the bottom needs to take this pile of bricks and stack them, in which case we'd call him a bricklayer. And he would use his energy in order to order that stack of bricks. That would decrease the entropy in the system. In order to decrease energy, we need an entropy, we need an energy input. Well, diffusion is a kind of entropy. Diffusion is where molecules will go from being in a tight cluster like a lump of sugar to being distributed all through a beaker of water, and so that's what we call dissolving. And dissolving is just a special case of diffusion. A perfume bottle that's opened up in a room and then over time the perfume spreads itself through the room is an example of diffusion, which is a kind of entropy. This is atoms going from a highly ordered state, all residing in this small space within a bottle of perfume, to going to a more disordered space where they're occupying the entire room and bouncing off of each other, or going from a highly ordered state like a lump of sugar to going to a disordered state like sugar dissolved in water in a beaker. We can see this in another one of these animations that I'm going to show now. And this is another animation from Wolfram. This particular one is called, it has a fairly complicated name. It's called a random walk and diffusion of many independent particles in an agent-based system. Or I've got it shortened to a bit.ly link that's just capital R random walk capital W-A-L-K. And so those are printed in your study guide. You can go to that, or you can watch the video, which I'm now going to show you with a little bit of narration that shows you this kind of random walk in diffusion.
This simulation also from Mathematica shows a random walk or diffusion of many independent particles. In this case, we have 100 particles inside a box, and as we start the animation, we're going to see them move away from each other. That's because each one of the blue particles here undergoes what's called a random walk. In other words, it's able to move about the container in whatever way it chooses. And so as we run the simulation, we'll see that there's more and more distance between the particles as each one goes through its random walk, until finally, if we let this go long enough, these 100 blue particles are going to fill up the entire box, fill up the entire container that they find themselves in. This is the process of diffusion. It's also called, in thermodynamic terms, an increase in entropy, an increase in disorder, an increase in randomness. This increase in randomness, this diffusional energy that we're going to use throughout the course to describe a lot of different physical processes. This is going to be very important for us as we get into Module 4 of cell biology, and as we get into the nervous system modules. Diffusion is going to be a force that we're going to become quite familiar with. And so we're going to need to understand this process of what we call a diffusional gradient or diffusional energy, where particles want to move away from one another and want to distribute themselves, starting at an area of high concentration and moving into an area where they're at lower concentration.